Assalamualaikum and hi. Today I am QISTINA ZULAIKHA with my fellow groupmates SYAZATUL SYTI KHAIRUNNISA. We present to you about organic chemistry with a topic benzene. So first of all, let's start with the definition of benzene. So what is benzene? Benzene is an organic chemical compound with the molecule formula C6H6C6H6. It is a colorless, volatile and highly flammable liquid with a sweet gasoline-like odor. Benzene is a simple aromatic hydrocarbon and serves as a fundamental building block in organic chemistry. Benzene consists of 6 carbon atoms arranged in a planar hexagonal ring with one hydrogen atom attached to each carbon atom. This structure is often depicted as a hexagon with a circle inside, symbolizing the locales and electrons that contribute to its stability and aromaticity. Benzene was first discovered in 1825 by the English chemist and physicist Michael Faraday. Faraday isolated benzene from the oily residue left after producing illuminating gas, a byproduct of the oil gas industry. The term benzene was coined by the German chemist Erhard Michaelis in 1833 after he synthesized it by distilling benzoic acid with lime. The name was derived from benzoic acid itself, named for gum benzoin, a resin known since antiquity. The most significant milestone in understanding benzene structure came in 1865 when the German chemist August Kückel proposed the benzene consists of a hexagonal ring of carbon atoms with alternating single and double bond. Kückel famously claimed the ring structure came to him in a dream of a snake biting its own tail. Kückel's model was revolutionary, but it couldn't fully explain benzene stability. Later, chemists like Johannes Thal and Linus Pauling refined the concept of aromaticity, introducing the idea of electron delocalization across the benzene ring, which provides additional stability. Benzene as a fundamental building block in organic chemistry. First, aromatic and stability. First, aromaticity. Benzene's stable aromatic ring structure, characterized by delicate and electrons, serves as a model for understanding aromatic compounds. Chemical reactivity. Benzene unit stability and reactivity patterns such as electrophilic aromatic substitution are foundational concepts in organic chemistry. These reactions are pivotal in synthesizing more complex aromatic compounds. Number 2 is synthetic intermediates. Platform chemical. Benzene is a starting point for synthesizing numerous derivatives, including phenols, amylines, and alkylbenzene. Functionalization. Benzene can be functionalized through various chemical reactions, nitration, sulfonation, alkylation, and etc., leading to a wide range of important compounds. Number 3 is educational significance. Learning tool. Benzene and its reaction are central topics in organic chemistry curricula, helping students understand concepts like resonance, hybridization, and reaction mechanism. Research foundation. Studies on benzene have led to the development of theories and models that apply to a broader organic chemistry. Benzene role in industrial application. Benzene role widely used in the industrial, especially in chemical industry, pharmaceutical, detergent, resin and adhesive, and dyes and pigments. So in chemical industry, usually it's used in a plastic and polymer industrial because benzene is a precursor which is polymerized to product polystyrene, a widely used plastic. It is also involved in the synthesis of raleigh and other polymers. Other than that, usually benzene also used as a drug synthesis because benzene derivatives are crucial in the synthesis of many pharmaceuticals, for example, aspirin. And then other than that, usually benzene also used in detergent, especially in cleaning agents because its derivatives are effective in breaking down oil, and grease, making them essential in household and industrial cleaning products. So basically, benzene role in industrial operation is widely used and usually used by these five common in industry. In dye and pigment, usually they use as a benzene derivatives are key intermediate in the production of synthetic dye and pigments. The aniline dyes, for instance, resolving the textile industry in the next century. So usually benzene is used by this industry. Environmental and safety consideration. Even though benzene is widely used, but it still have its toxicity. So usually this is what health risks that always happen whenever we use benzene. First is the toxicity. Benzene is recognized as a carcinogen and exposure can lead to serious health issues, including leukemia and other blood disorder. Regulation. Industry use of benzene is heavily regulated to minimize exposure and protect work health. Safety measures include personal protective equipment PPE, proper ventilation, and strict exposure limits. Number 2 is in environmental impact. Pollution. Benzene is a volatile organic compound VOC and can contribute to air pollution and groundwater contamination. Mitigation. Industries are required to implement measures to control benzene emission and prevent environmental contamination. Structure of benzene. Benzene is a unique organic compound characterized by its aromatical and hexagonal structure. Understanding its structure is a crucial for grasping its chemical properties and reactivity. So benzene structure, first is because it has a hexagonal ring. Benzene consists of 6 carbon atoms arranged in a hexagonal ring. Each carbon atom is bonded to one hydrogen atom, making a total of 6 hydrogen atoms. Number 2 is a bonding and dealkylation. Traditionally, benzene was typicized with alternative single and double bond. However, this is a simplified representation. In reality, benzene structure is best described by the concept of electron dealkylation. The 6 and electron from the double bonds are dealkylated over the entire ring, forming a continuous electron cloud above and below the plane of the ring. Number 3 is resonance structure. Benzene is often represented by two resonance structures which show the alternating double bond in different positions. These structures are not real, rather they represent the delocalization of the electrons. To emphasize the localization nature of the electron, benzene is often described as a hexagon with a circle inside it. Planar geometry. Benzene is a planar molecule, meaning all its atoms lie in the same place. This planarity is due to the sp2 hybridization of the carbon atoms. The bond angle between the carbon atoms are 220 degrees, typical of sp2 hybridization carbon atoms. Bond lengths. In benzene, all carbon-carbon bond lengths are equal at approximately 1.39 A. This is interminable between a typical single bond, further illustrating the concept of delicate bonding. Resonance and stability of benzene. Benzene stability and chemical behavior are significantly influenced by the concept of resonance and electron dealkylation. First is resonance structure. It's because of Köhler structure. Benzene can be described using two resonance structures. Each structure shows alternative single and double bond around the hexagonal ring. These resonance structures are not distinct molecules but rather a way to represent the dealkylation of electrons that are equal energy and then to represent the true structure of benzene by itself. Number 2 is the localized electron and electron cloud. Instead of having localized double bond, benzene 6 and electron are shared equally among the 6 carbon atoms, forming a continuous electron cloud above and below the plane of the ring. The dealkylation lowers the overall energy of molecule, contributing to its stability. Stability of benzene. Number 1 is aromatic stability. Aromatically, benzene is an aromatic compound, which means it follows Hacker rule for n plus 2 n electrons, where n is an integer. For benzene, n equal to 4, giving 6 n electrons, which are delocalized around the ring. Planarity. The planarity of benzene allows for maximum of the p orbital facility in electrons delocalization and enhances stability. Number 2 is resonant energy. Number 2 is resonant energy. Experimental evidence. The resonant energy of benzene is the difference between its actual energy and energy of hypothetical molecule with localized double bonds. This energy difference is significant, indicating benzene's exceptional stability. Hydrogen is an example. When benzene is hydrogenated to form cyclohexane, the process releases less energy per double bond compared to another alkanes. This is because benzene is already lower in energy due to a resonance stabilization. Chemical reactivity. Substitution reaction. Benzene tend to undergo electrophilic aromatic substitution rather than addition reactions, which will disrupt its aromatic stability. This reaction third preserves the aromatic ring by substituting a hydrogen atom with another group without affecting the delicate electron system. Resistant to addition. Alkanes typically undergo addition reaction with halogens and hydrogen halides, but benzene is resistant to such reaction due to the stability of its aromatic system. I think that's all.
So now we want to talk about physical properties of benzene. The appearance of benzenes are colorless and volatile liquid. Boiling point for the benzene is 80.1 degrees Celsius. Density of the benzene is 0.8765 gram per cm3. And the solubility of the benzene are insoluble in water and soluble in organic solvent. Next, chemical properties of benzene. Chemical properties of benzene has 2 points. First, reactivity, and second, toxicity. Reactivity undergoes substitution reaction rather than addition reaction, preserving its aromatic ring. Common reactions include nitration, halogenation, and sulfonation. And then toxicity. Benzene is carcinogenic and exposure can lead to serious health effects like leukemia. There are two types of industrial production of benzene. First, sources, and the second one is global production. For sources, produced primarily from petroleum and charcoal tar. And then, key processes include catalytic preforming, toluene hydrodealkylation, and the steam cracking. For the global production, benzene is major industrial chemical with millions of tons produced annually. So here we have two types of application of benzene. First, chemical industry, and the second one is consumer product. For the chemical industry, used as a precursor to make other chemicals such as styrene for plastic, phenol for resins, and aniline for dyes. For the consumer products, is found in some rubbers, lubricants, dyes, detergents, drugs, and pesticides.
So we talk about industrial application of benzene. Okay, so the first one we have a chemical synthesis. Benzene is an important procedure to numerous other chemical and polymer compound. In organic chemistry, benzene is a very important raw material for many chemical companies to create industrial chemical like ethylbenzene, which used to make acid and acetone. The chemicals are used in turn to create a wide variety of useful products. So what we have in a chemical synthesis which is plastic and resins. Okay, benzene is used to produce styrene, which is polymerized into polystyrene, a widely used plastic. It is also involved in the production of phenol and acetone, which are key components in the manufacture of polycarbonate plastic and epoxy resins. Okay, next one is a synthetic fibers. Through various intermediates, benzene contributes to the production of nylon and polyester fibers, which are essential in the textile industry. Okay, next is a rubber. Benzene is a precursor in the synthesis of rubber and rubber-based products, crucial for automotive and industrial application. Last one is a dye and detergents. Many dyes and detergents are synthesized from benzene derivative, highlight its importance in the chemical industry. Okay, for the next slide is a solvent. Benzene solvent properties make it useful agent in laboratories in an industrial setting. It effectively dissolves various substances, facilitating chemical reaction and process despite its toxicity. It has been historically utilized for extraction and purification. Benzene is employed in the extraction of oil and other organic compounds, as well as in the purification of chemicals due to its ability to dissolve fats, oils, and resins. Next one is a reagent and intermediates. In chemical research and development, benzene is used as a reagent and as an intermediate to synthesize the other chemical. Okay, the last one of this industrial application of benzene is a fuel additive. Benzene was once commonly used as an additive in gasoline due to its high octane number, which helps to improve the efficiency and performance of engines. However, its use in a fuel has been significantly reduced and regulated due to health concerns. Okay. Historical use. Benzene was added to gasoline to enhance its octane rating, which helps prevent engine knocking and improve combustion efficiency. Next is a health concern. Prolonged exposure to benzene is linked to serious health risks, including leukemia and other blood disorders. As a result, regulatory agencies have imposed strict limits on its concentration in gasoline to protect public health and reduce environmental pollution. Okay, next we move to the next point, which is modern research and development. Okay, the first one is a sustainable chemistry. Effort in sustainable chemistry focus on finding greener alternatives to benzene and reducing its use to minimize environmental and health impact. Key development include recycling and recovery. Technique for recycling and recovery benzene from industrial process are being improved, reducing the overall demand for new benzene production. Next is a green chemistry principle. Researchers are developing processes that use renewable resources and environmentally benign solvent instead of benzene. For instance, biomass-derived chemicals are being explored as replacement for. Okay, for the next one is an advanced material. Benzene derivative play an important role in the development of advanced materials such as graphene, which have significantly technological application. Graphene synthesis. Benzene is a precursor in the chemical vapor deposition (CVD) process used to synthesize graphene. Graphene, a single layer of carbon atom arranged in a hexagonal lattice, has exceptional electrical, thermal, and mechanical properties, making it valuable for electronics, composites, and other advanced applications. Nanotechnology. In nanotechnology, benzene-based molecules are used to construct carbon nanotubes and other nanostructures, which have application in drug delivery, material science, and nanoelectronics. The last one is a medical chemistry. The benzene ring is a fundamental component in the structure of many pharmaceuticals, contributing to their biological activity and efficiency. Pharmacophores. Benzene rings are often part of pharmacophores, the active parts of a molecule that bind to a specific biological target. The aromatic nature benzene allows to pi stacking, interaction, and hydrophobic contact, which enhance the binding affinity and specificity of drugs. Next is chemical modification. Medical chemists frequently modify benzene rings to improve drug properties such as solubility, stability, and bioavailability. This can involve adding functional groups to the benzene rings or incorporating into larger, more complex structure. Okay, so for the conclusion, summary of this topic is the molecule of benzene is unique due to its structure and properties. It plays a key role in organic chemistry. The 6 carbon atoms of its simple aromatic rings are hexagonally arranged in a planar manner, giving rise to stability and reactivity essential to a wide array of chemical activities. Benzene is a key ingredient in the production of hundreds of different chemicals and materials. It has even found use in laboratory and industrial application because of its solvent properties. Although benzene has a major industrial significance, it has risks from exposure, including several causing fatal via choking, and it's known to be carcinogenic by being on the list of International Agency for Research on Cancer. Severe precautions still need to be taken in handling or using this compound relevant ratio. For the future outlook is we hope it have a safer handling practice, advanced material development, and alternative compound. The references is by book Organic Chemistry by Paula Y. Bruce, Advanced Organic Chemistry by Jerry Marsh. An article include a few key journal article or review, and for the website is a reliable chemistry resources like the American Chemical Society website. So that's all from us. Thanks.